Hello everyone and welcome to Handmade Hero, where we code a complete game live on stream. We have to go do some Huffman decode stuff today. Basically we are, so we're implementing the PNG spec, and we did most of the sort of outer parsing stuff, and now we're doing the deflate portion, which is probably the hardest portion to get right, I'm guessing, based on the spec, because it's kind of got the tweakiest stuff, would be my suspicion. So, you know, it's not a particularly fun or interesting part of things, but it's just what you have to do if you're going to read compressed stuff. So there's not much more to say. That's just what we're doing. And so here we go. I'm going to go ahead and load up our PRJ here. I'm going to compile that. And here's our PNG reader as it stands right now. And when last when we kind of finished this up, we were in here and starting to, I want to move this. This is behind my head, and that's not gonna fly. We were starting to sort of decode the rather squirrely stuff that happens inside the deflate portion of the PNG, which is right here. And we have just a little kind of crappy thing we wrote that gives us bits at a time. And the only reason we did that is for convenience at the moment, because this spec happens to be written bit at a time. Anything that's Huffman encoded is obviously going to be bit at a time, because the whole point of Huffman codes is that you only read as many bits as you need to decode a symbol. So the easiest way to implement that before you start looking at things like how to run more quickly or something like that is to just go ahead and make it so that you can read a bit at a time and actually implement it literally. Even though that's probably not what you would want to do if you were doing a fast PNG compressor. We're not particularly trying to do a fast PNG compressor here. We're just trying to make one that works at all. Okay, so back to our friend, the specification. If you look in here, we've got sort of the compression method stuff that we were reading in the PNG. And basically, if you remember, it just referred us to somebody else, right? It was kind of like, look, when you get to the actual data, we don't want to specify how that works. We're just going to use some other thing that already exists. So go read the deflate spec, which is an LZ77 derivative. That's how we stored the data, right? So it's like, okay, let's go ahead and do that. And so I believe this is also not relevant to us, right? Yes. So I believe all we really care about is this stuff in here. Yeah. So here's our deflate spec, and this is what we were working with. What we were told by the spec is that we would get information here that told us how to construct the Huffman tables for reading the Huffman tables. I know that sounds a little weird, but in order to save space when they were tweaking, one of the things that happens with compression, right, because you're trying to figure out how to compact the most number of things efficiently, you end up having all kinds of tweaky weird stuff that you just found happened to be locally optimal for the kinds of stuff that was in your corpus, right? They call things a corpus, a body of work, basically. They call things a corpus, which is basically a set of things you test with your compressor on to see how well it does. So what typically happens is people make a compressor, they run it through a corpus, they see how good the compressor is, and then they tweak parameters in the compressor to try and continue to get higher and higher compression ratios on that corpus, right? So that's why you get things like this, where there's some kind of a prescribed table in here that says, look, we're going to send you some number of code lengths, and then we're going to only send you as many of them as we think that you need. And the order we're going to send them to you is not 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. It's 16, 17, 18, 0, 8, 7, 9, 6, 10, 5, 11, 12, right? And why is that there? Well, the reason that's probably there was because they just kept tweaking the order of things in those tables until they found the one that allowed them to truncate the series as early as possible on the most number of files, right? So tons of stuff is like that. Like, why is this 5 bits long? Well, it's 5 bits long because they needed to be able to specify something up to 32, and that was because that was the most that they needed for figuring out how far back something should be for the length of something, because on the data they tried 6 bits, and 6 bits ended up costing them more and not saving enough, and blah, 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 right? So who knows? Like, all of the stuff in here basically went that way. That's how compressor work is. That's how people make compressors, right? Is they keep looking for more ways to save a bit here, save a bit there, until they get it down to what they think is the best they can do for that particular design, and that's what you end up with. So that's why we have this kind of weird, torturous, relatively obtuse thing going on. It's not because the people who made this compressor were stupid or hated us. It's just because that's the nature of compressors, and this is also a very old compressor, so not only is it the nature of compressors, they also were doing it in 1996 when this was probably the best they could do. Nowadays, there's probably a lot of other things they could have done that would have been better. They didn't necessarily know about them. But a lot of times that even makes them even more complicated, so it doesn't necessarily mean it would be simple. It just means that if you see them going through a lot of lengths to do something that seems like it's not that great, well, don't forget it might have been the best thing they knew about at the time, even though there's probably better things that they could have done today. So let's get started on this part here. This is the part that we actually need to start working with. What they sort of said is we want to... Oh, sorry, I'm circling the wrong part. I meant this part. So what they took a long time to explain early on in the spec, and we haven't actually dealt with yet, but it is what we actually need to do, is they told us that the way they were going to write Huffman codes out was rather than store the code, because the code itself is what we actually need to know, but rather than writing out the code, they were just going to write out how long the code was. And the reason for that is because writing out how long the code was is a lot less bits than writing out the code itself, right? Because, for example, if you need to write out a 4-bit code, that takes 4 bits. But if you only need to say that a code is 4 bits long, that only takes 3 bits, right? So, again, compression. So rather than specifying what the codes are, they just want to specify how long the codes are. Why do they only want to do that? Because it saves a little bit of bits. How does that possibly work? Well, it works because they don't care which code gets assigned to which symbol. They just care how long the code is that gets assigned to the symbol. So the order of assignment is arbitrary, which means they're free to pick one that is easy to determine without knowing anything other than the length. So if we order our symbols from smallest to least, from least to greatest, like this, A, B, C, D. If we just know the length of the code, then it's trivial for us to put that code in because there's only one code it can be at any given time, right? If we know that the code 110 always precedes the code 111 because we always put lower codes before higher codes, then you don't need to tell me which of C and D is this particular code. You just need to tell me that they're both 3 bits long, and then I know the first one will be 110, and the next one will be 111, right? All makes good sense. Like I said, it's probably a stupid thing to do now because you wouldn't even use a Huffman code or something like this. I don't know, ask Charles Bloom, he would tell you. But that's what they use, so that's what we have to do. And it makes reasonable sense for what they were trying, right? So what we need to do is we need to follow this pseudocode that they've specified here, count the number of codes for each code length, and let BL count be the number of codes of that length, right? So we're just going to go through, if we're following this pseudocode, we're just going to go through all of the lengths that they told us, and we're going to just remember how many of each one we saw. This is a histogram, basically, right? It's saying for every time you see 5, add 1 to the 5 column, right? Every time you see 2, add a 1 to the 2 column. And it just gets, a little histogram of how many of each we've seen. Then it signs, find the numerical value of the smallest code for each code length. So that's just looking at where it starts, right? Then it says, assign numerical values to all codes using consecutive values for all codes of the same length with the base values determined at step 2. Codes that are never used, which have a bit length of 0, must not be assigned a value. All right. So that's all we need to do. There's probably some subtlety there, we'll see in a second, but they've laid out a very clear course of action for us. If we just implement what they say, hopefully we won't get too many snafus on the way, but I don't know, we'll see. So what I did when we were doing it before, and I didn't really know what we were necessarily going to have to do there because we hadn't looked at it in much detail, we have these sort of PNG informational things that we've been using, and then we've got this guy here, which is the PNG Huffman. Technically, this isn't part of the file format, so I can actually move that out here. These are all in the file format, right? Whereas PNG Huffman is not. So these guys can actually be sort of like, if that's the file format, this is sort of the utility functions, right? So this PNG Huffman here is what we need to use to sort of store these counts, and we want to make something that can like store the counts and then process the counts, right? Like, so what you can see here is we've got one, we've got this sort of thing going where we do HClen swizzle. To be honest, I don't know if I really need this PNG Huffman thing because we probably don't actually need that. I may have been a little premature here to do this. This probably doesn't, this probably can be something that's just an array, but we'll see in a second. Anyway, so what you can see here is like we go through the HClen swizzle thing, we swizzle the bits that we consumed into that, and then this is the first time we have to do one of these Huffman codes. So what we were doing is the HClen swizzle was taking the bits that we read in. We know we have 3 for each of the filled in indices, and we're going to assign them that way. So now we're going to end up with swizzle data into a thing that's as long as hclen. It's the hclen table. So as long as hclen swizzle, some of that hclen table has now been filled in with lengths. Possibly all of it, but we possibly, because we read a, remember we read a length here, this right here. We read a length. That length says how many of these we had, so we may only have the first n, and then there's just zeros everywhere else, right? So then what we're going to do is we're going to want to do our first Huffman table generation here. So we need something that's going to create a Huffman out of this. Okay? So when we go to do the compute Huffman, hclen is not really what we want here, unfortunately. I think I probably did that a little bit incorrectly. This is actually this. Because remember that, so the way we're doing this is we have a set of symbols. Excuse me. We have a set of symbols. We've unpacked them into this table, right? And now what we want to do is we want to go ahead and take that table and we want to scan through the table, and there'll be zeros where there's symbols that aren't used and actual values where there are symbols that are used. So we need to go through the whole table. We can't just go through hclen, because if we only went through hclen, we would probably stop before some values that actually had stuff. How do I know? Because actually the high values occur very early in here. So even if the value was only 3, we would fill in like the 18th element, right? Which is like the last element of the thing. So we know that we have to process the whole table, so we really want to do a compute Huffman on that. Here's the table, right? And then we want to produce a Huffman out of it. So what we could do is start to fill in this function, and then also we want to sort of think about how we implement Huffman decode. And that way we can sort of start to figure out what this PNG Huffman thing will be used for. So I have literally never written a Huffman decoder before, so I have no preconceived notions about how you would do it. I'm sure the way I do it right now will not be particularly good, but that's okay. Like I said, this is just entirely about showing how to implement something from a spec if you have no idea how the thing works at all. To be fair, I do know how a Huffman code works, so technically speaking, I guess I do know something, but I don't sit around implementing Huffman decoders, so it's not like I'm like, oh, and then this is just the way I like to implement Huffman codes. I make a table that looks like this and something, right? That's not what I would normally do. So anyway, let's go ahead and take a look at this part further, and then after we do the basic step of producing the table, then we have to think about how do we want to actually store once we know what all the codes are, how do we actually want to store this so that we can decode them efficiently? Because there's a couple different ways I can think to do this. One way is if we know that the codes are always small enough, we could use a direct lookup, right? We could basically do something where all of the possible values that have... I'm not... This is just me like thinking out loud. I'm just going to say it so you can see what I was thinking of. So let's say we wanted like a really fast way to decode Huffman. Really fast is not the right term. Let's say we wanted a really straightforward but somewhat efficient way, right? So let's say I wanted to make a really stupid Huffman decoder. So there's two ways I could do it. One way is to make the slow and stupid. And that's basically like literally read one bit and literally have like a node that just says one thing or another, right? So we literally build like a tree and we read a bit at a time and go down the tree, right? That's like the slow and stupid way. But there's probably a like fast-ish and stupid way that I'm just thinking in my head here, which is that let's say we know our Huffman code is bounded. So we know that there are no Huffman codes that are longer than, let's say, 7 bits long or 8 bits long, right? So we know that 8 bits is the longest code we will ever see. Because probably in the spec somewhere where we're looking at it, there's probably just, it's never going to be longer than this. Because there's, even if we assign symbols maximally stupidly, we would only have this many or something, right? Well, if that was the case, we could make an 8-bit lookup table, right? That just had, okay, if 0 outputs an A, right? And 1, 0 outputs a B, and 1, 1, 0 outputs a C, and 1, 1, 1 outputs a D, right? So when we read a 0, we output an A. You know what? I wrote those kind of backwards because I should be going LSB probably at the moment. It's hard to say whether it should be left to right order or right to left order here. But so like first, second, third, let's say. So this is the first bit that comes in. This is the second bit, right? So if I see a 0, I just output an A immediately. If I see a 1, I know I have to look at the next thing. So if I see a 0 there, then I output a B. If I see a 1 and a 1, then I know I look here for one of 2 different bit values, then I get the C or the D, right? So let's say that's my Huffman code, right? And maybe that goes out to 8 bits long eventually or whatever. Who cares, right? Well, what that means is I could just read this number of bits. In this case, it's like 3 bits, right? So it would be like a 3-bit LUT. And what I could do is I can just put A's in all of the slots of the table that have, for all of the different combinations that would be here. So a 3-bit lookup table is actually 2 to the 3rd long, right? Which is 2 times 2 times 2, or 8. Now there aren't 8 symbols here, so what goes in the 8 tables? Well, the 8 things are this, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Here's all the entries. So we know some of them. We know that 0 was A. We know that 0, 1 was B, right? We know that 1, 1 was C. And 1, 1, 1 was D. So what do we put in the rest of the table? Well, just imagine if we read out 3 bits, that means that anything else we saw here or here still codes for an A, and we want to just shift down 1 bit. So we put in here an A and only take 1 bit, right? Then into the other parts of the table that also have a 0, but have arbitrary other things up here, we also put A, right? I'm just imagining this in my head. I'm just thinking this through. Again, I've never implemented Huffman. I'm just talking out loud about one way I could implement a Huffman table that came to me as I was reading the spec. Right? So each time I write down what symbol it is and how many bits to shift out of the output, right? Same thing with B. I know that could be one of two things here. So there's one B, here's the other B. And that time I say take 2 bits each time. Then for the C's and the D, I say take 3 bits, right? Here's my complete Huffman decode table. What I do every time is I just look up a 3-bit value based on the 3 bits I currently have. I output the symbol it tells me, and then I shift off however many bits in my current value it tells me, and then I do the same thing again. I fill in the bits that I'm missing, and I go again, right? Make sense? Very simple. So I'm just thinking in my head, how am I going to implement this, right? And that's one way I could do it. And that would allow me to do it with just one lookup. So I don't need to go down an actual Huffman tree looking for a node, which would be this like annoying kind of, skip list thing. I could instead just do this, and then I just look up in a table and I get the symbols, output the symbol, shift, right? I don't know what you want to call this. Let's call it the LUT and shift algorithm. Patent pending 2018. Registered trademark, TM. So I don't know. So that's what I'm going to say is the way I might try to do it, assuming that the lookup tables aren't too big. Because it seems pretty efficient. Now, the problem with this is if the symbol length ends up being like 16 bits, then I've got a 64,000 entry lookup table is not cool, right? 64K lookup table is not cool. And probably not what I want. So I'm guessing that there's a limit to this LUT plus shift algorithm. Yeah, your mileage may vary. I feel like we could make a adjunct to this, like say like we did have to do 16 bits. I feel like there's probably a way to do it that breaks the thing down by just using a tree for the top few bits and then a LUT when you get down to 8. You know what I mean? So we probably could do something like this even if the codes get long, but I'd have to think about it some more. My super patent pending awesome algorithm, which is not that awesome, is probably amenable to something like that if we needed to extend it. All right, so with an eye towards that, I guess the other thing that I'd say is, so do we actually know what the maximum bound is on the stuff that we're looking up into these tables? Because I don't really know I don't know the answer to that question. So it'd be interesting to see in here if that's like made clear one way or another, and so we could see. So let's see. Here's them talking about the Huffman code. So it says, it says here it cannot exceed certain maximum code lengths. So that suggests to me that somewhere in here for every one of these, someone should state what the maximum code length is, right? That's just talking about generically how we do it. Blah, 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 blah. Don't care about that. Don't care about that. Let's see. Encoded data blocks of deflate format consists of sequences of symbols drawn from 3 conceptually exact literal bytes, byte values, or length backward distance pairs, where the length is drawn from 3 to 58 and the distance from 132,768. The literal and length alphabets are merged into a single alphabet, 0 to 85. Let's see. So actually, now that we look at this with an eye towards my patent pending algorithm there, it looks like they actually already did it for us, right? That's exactly what this thing is. They've got a Huffman for the first part, but then they stick extra bits to get the rest, right? So it looks like they already broke it into a small Huffman table for decode, guaranteed, and then for larger ones, they didn't Huffman those. They just put in some extra bits, right? So that's pretty good. We're not doing fixed Huffman codes because that's not allowed in the PNG, it sounds like. So we're only doing these. And it says, let's see, first, each code is defined with sequence of code lengths for even greater compactness, blah, blah, blah. Don't care about that. The next 2 bits repeat the length. So this is not our concern because these lengths are going to be smaller, presumably, than the other lengths are, I would assume, because 0 to 18 is a really small set of symbols. Blah, 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 blah. Black. Don't care about that. Huffman code. So where are they going to talk about the maximum code lengths? They have not stated the maximum code lengths. They said what the maximum values are, but they haven't said what the maximum code lengths are, as far as I can tell. Compressor may limit further the ranges of values specified in... Oh, well, you know what? No, they have. So this tells us, right? So it's 3 bits for the code length of this, right? And so for each one of these, it can only be 3 bits worth of symbol, 3 bits worth of length. So that means it can't be more than 8 bits, right? I'm sorry, the code that it's talking about can't be more than 8 bits. So that's pretty straightforward. Code lengths for the using the code length Huffman code, and so that's like code lengths of 0 to 15. Copy the previous code length 3 to 6 times, repeated length. So that looks like the maximum code length is 2 to the 15th, or 32K. Of values, right? So that would mean if we did want to do what I'm talking about with a lookup table, it would be a 32,000 entry, well, 32K entry table, which is fine. I mean, honestly, even a 16-bit lookup table, I said that before without even thinking about it, but it's 64K entries. If every entry we're talking about only is like 8 bytes or something, I mean, you're not even cracking a megabyte, right? At that point. So if we're talking about 2 to the 15th, storing something like 8 bytes, which I don't even know if we need that many, that's like a quarter meg. And even if it's only a half meg. So I guess my algorithm there is just fine. It's probably not the right one to use. Charles Bloom right now is rolling over in his task chair as I'm about to write this, I'm sure, but seems fine. So I guess what I'll do is I'll just do the algorithm I just said. I mean, why not, right? Seems like the easiest thing, and it would just work, right? So that basically lets us know that like a PNG Huffman. So we probably don't want these PNG Huffmans sitting around on the stack though, because that's going to put a lot of stack pressure on for no real reason. Now, probably is okay, but it just seems a little more sensible to maybe allocate those. It just seems a little bit a little bit more reasonable, right? So what we probably want here is something that's just like allocate Huffman. And when you allocate the Huffman table, maybe you tell it how, like, what you're expecting to be the maximum symbol size there. So, you know, we could make them all, because we know that 15 bits appears to be the maximum size, we could make all of them be 15-bit wide, but why bother allocating memory? You don't have to. We might as well just use however many bits the person says they need, because we know that there are other places where we're going to be decoding things that have a lot less bits than that. For example, one of them only had 8 bits maximum, so there you go. So max code length in bits, right? So then when you do that, in here we can have a PNG Huffman entry, and the PNG Huffman entry is just something that tells us what the symbol is to retire. So we've got the symbol in here. Now, the symbol, I don't know if we're always doing bytes, so I'm going to leave it as a U32 for now, but it may be that we always decode bytes at a time, and we don't encode anything bigger, but I think we encode sometimes things that are bigger. So what we want to do here is probably say something like symbol and symbol length, right? And then this can probably be split into two things, like so, which is the symbol length and the bits used, right? So what I'm saying here is that, like, okay, we can store up to 4 bytes worth of symbol, which is probably the maximum that we're ever going to be asked to decode. I think the maximum we're actually asked to decode is actually less than that. I think it's like 16 bits or something. I don't remember. We'll look at the spec to go through it. But I'm pretty sure we wouldn't need any more than that. So this is like just an 8-byte structure that has 4 bytes worth of symbol, a length that tells us how much of the symbol we actually use, because symbols could vary in size. One symbol might be only 8 bits long, another one might be 16 bits long, I don't know. We might not need that, in which case it can be pulled out here. And then we have a bits used. So we could bring this down to even shorter. You could imagine if we wanted to, we could have something like this eventually, if we know if it turns out that our symbols are always U16 or less, then what we can probably do here is just say, look, we can make this just a 32-byte entry. I'm sorry, a 32-bit entry that just has the symbol length, the bits used encoded in half the space, because really the symbol length and bits used only need 8 bits anyway, no matter what's happening. So in fact, they could be even less than that. So we pretty much know we could always go a little bit lower. We could probably even do something if we really wanted to get down to it. If we knew that all of our symbols were bytes, which we don't, I think, know that. So I think this is too small, but we could do something like this. Right, and that would get us down to only 16 bits per entry. Again, doesn't matter. We can use the large version, and it will not hurt us, I don't think, because there's just not going to be that much of a performance thing going on here. We are not trying to make a high-performance decompressor, but it's just worth noting, like, depending on how big the symbol needed to be, we could go down as low as 16 bits without anything fancy. If the symbol's small, we could go as low as 16 bits just trivially by packing the symbol and bit lengths into 2 nibbles. Right, anyway, moving along, we know that the PNG Huffman just has a PNG Huffman entry here that's like all of the entries that it's got, and then we've also got a thing here that probably says what the entry count is. And so when we actually have this allocator, what we're going to do is say, well, whatever the maximum code length is in bits, that's going to tell us how many entries we have, because the power of 2 on that length is the number of entries. So if they tell us the max code length in bits, is 12, then we know that 2 to the 12th is going to be how many entries are in our table. Because we know this code is being kind of piggy and inefficient here by just allocating as many entries as it needs without thinking about it, I'm going to put an insertion in here that the max code length in bits is not going to exceed 16 in any cases, because if someone came along and tried to use this for something that had 24-bit Huffman codes, this is probably not the right way to go, and they should probably get an assertion to let them know that. They're free to turn it off if they want to roll the dice, but it's probably just a bad way to do it at that point. My patent pending algorithm obviously is super awesome, just like all the other things that people patent in software that are so difficult to figure out. You know, parentheses, almost all of them are very easy to figure out. Anyway, so if we go ahead and do our Huffman allocator here, what we can do is just go ahead and say, all right, let's make the result here. The result's going to have an entry count that's proportional to the max code length in bits, like I was saying. So what we do is we take that and we just raise it to the power of 2. So by shifting a 1 up by that many bits, we know how many of these we have. So if we have like 1 bit, we have 2 entries. If we have 2 bits, we have 4 entries, and so on. Then we just allocate an array that's proportional to that, because we say we need that many entries. So we just take that number that we've already computed, and we malloc a number of entries proportional to that. So the number of Huffman entries we have, we now know. We mallocate PNG Huffman for every one of those entry counts that we have, and that gives us our complete structure, right? Now, we don't want to fill any of these in because what we're about to do is actually, you know, generate this from something that is going to figure out exactly how the table should be filled out. And so we just leave it at that. Like, that's the allocate Huffman. Then what we want to do is later on, when we go to actually compute a Huffman, which is this thing here, we need to actually take one of these PNG Huffmans and do what we're going to do. Now, oops, I got some backsplash there. Now what we need to do for the PNG Huffman decode is actually now really straightforward. So the compute Huffman is kind of a little more squirrely because we got to go follow that nonsense stuff in the spec where they had all the weird, like, okay, count the code lengths and then assign this way, right? We can go do that. It's not going to be hard, but it's going to be error prone and we might screw it up. So it's going to be an annoying thing to write. It's fine. So let's write this first because we kind of know what we're actually doing here. So when we do the Huffman decode, when we bring that symbol back, off we go. Now, I think when I'm looking at this here, the way that the Huffman decode works, it looks like we don't really need the symbol length necessarily because the symbol itself looks like it's the length. Because everywhere, now I think about it, everywhere that we decoded the Huffman, I think we never need to know the length. Now let me just explain what I mean by that. So there's 2 ways you can encode symbols. One is that they are bit symbols, and one is that they are like numerical symbols. So a bit symbol is like 00101111, right? A numerical symbol is not that. It can only be like that, right? So a numerical symbol can't have leading zeros. Why can't it have leading zeros? Because the number, 14, there is no number 014, right? There's just 14. And if you want something in this place, it can't be a 0. So zeros only happen after the first valid decimal. They don't happen before, right? Bit symbols, there's no such constraint. I can trivially talk about the bit symbol 00101111, that's not a problem. I cannot trivially talk about the number 04932, right? That's not a real number in our system. So it seems like everywhere I'm decoding Huffmans, they're real alphabetical numeric symbols like that. Now I think about it. So I think that means I don't need to know the symbol length. If I didn't have that constraint, I would need to know how long the symbol length is because I couldn't just look at the symbol and know that the zeros can just be ignored at the front, which means that the symbol length is implicitly encoded in the symbol itself. So I think actually this can be simplified, right? It could be simplified down to symbol and bits used, which means that if we are fortunate enough to know that the symbols are always 64K and less, we can just go with something like this, which I think they are. So let's just say that that's the case for now, and go with this, because it looks like the bits used is the only other thing that we need, and so we can just make each one of these be 4 bytes long, and then we know that our table is going to be like, you know, a quarter megabyte, which is like a nothing burger for any modern CPU. That'll be sitting in the cache, L2 at least the whole time, so it's all fine. So anyway, what we want to do here is go in the Huffman decode. I know I've got to return a particular value here. That value is going to be whatever the symbol is that I end up with from my entries. So what I need to do is I need to look at the streaming input buffer. I need to make sure that I have enough bits to do one PNG Huffman. And if you remember correctly, what we've got here in the streaming buffer is a thing that says like a bit buff and a bit count. So what I want to do there is I want to make sure that I can peak the bits, and so I can always just look at them without consuming them yet, right? So rather than doing a consume bits, what I want to do here is expand this function to an ensure bits, right? Which just says this is how many I want, or maybe a peak bits, something like this. And so what that's going to be is it's literally the same function, right? It's exactly the same function as consume bits, only it doesn't shift the bit buffer down, right? So normally we've got this thing in here that shifts the bit buffer down, and when you shift the bit buffer down, you're basically consuming the bits off. So if I just want to peak, all I do is not shift it down, right? So that update there just doesn't actually do that shift. So then what I can do here is say, all right, here's the peak bits. It tells me how many I get. And then what I can do is do a like discard bits. And I can say how many I want there to be. Like so. And so in this case, we can basically have a peak bits call, which fills the bits up to the amount that needs to be there, ensures that many are there, and then assuming that it gives you back the result that you asked for, that's the number of bits there. And then I can discard bits from that as well, right? Then what I can do too is I can do the discard bits, which is this part of it. So what I can do here, if I want to, is I can write consume bits in terms of peak bits and discard bits, right? So a consume bits is just a thing that's like, oh, okay, the result equals the peak bits of the bit count, and then discard that many bits. Right? And that's pretty straightforward. Now, what we might want to do is set an error flag here if we use too many bits on the streaming buffer, so we just remember when the bit buffer has run out, if that makes sense. So we could say in here that like the streaming buffer has a thing that just says, look, if the thing underflowed, you know, we can say that. So in here we could just say like, yeah. You know, we ran out of stream. You were telling us to decode something, and you know, we ran out. Sorry. So we could do that. I don't know if we actually want to do that because we may want to read at the end. We're still going to try to read an entire Huffman symbol, and that symbol may be short. So I don't know what we want to do about that exactly, I guess is the way I would put it. It's kind of a little confusing. So we'll see. But anyway, we can set the underflow to true there if we want to. That allows us to know whether we've hit some kind of a failure case. And then what we can do is, now these are pretty clean, right? We just like say peak bits. If we need to fill the buffer, we do. If we need to set the underflow flag, we can. What I can do there is say, look, the underflowed flag is always going to be just something that tells us if we underflowed, like so. And then that way this doesn't have a branch in there for no reason. So we just set the results always equal to the mask off of the bit counts. We always set that, and then we just set the underflow to whether or not the bit count actually could have supported that many. Pretty simple. Then on the discard bits, we just actually try to discard the bits. We only need to discard the bits if we can, so it's like a flush to zero thing. We maybe don't actually need to do that. We could just always run this because underflowed would have already been set. So we would know that we underflowed and we maybe just don't care about this then. So that's kind of hard to say. I don't know. Like, probably we can just do this. Because it's like once you underflow, who cares? The rest of the data you're going to get is garbage, so it doesn't matter, right? So maybe that's fine. I don't know. That's what we're looking at. All right. So at that point, this is pretty branchless, except for this part here. And that's because we wrote this generic for the bit count. We could make one of these where you actually say how many bits you want as part of the function call, and then this would be completely branchless. It would just go, right? And so it's kind of you can see why people like Huffman stuff. It's probably pretty easy to write a nice little efficient thing that just goes, oh, let me shift some bits and have a party, right? Okay, so now that we're done with that, let me just compile this here and move on. So now that we're done with that, when we actually want to do a Huffman decode, this becomes pretty straightforward, right? You can see where I'm going with this. We know how many bits we want because our Huffman can tell us that, right? Bits per symbol is something that, bits per. This is the thing that we got passed in. It's a really ridiculous long name. That. So what we want to do here when we go to do the Huffman decode is I'll just say, oh, yeah, just give me that many bits, please, from the input. We'll look at that value, right? Then we want to assert that that value that we're going to jump through here, like we're not jumping, but we're going to look up through here. We want to make sure that that doesn't overflow because it should be possible for us to do that, right? There should be no way for us to ever get back a value here with only that many bits that's not going to overflow the entry count. But again, we would get exactly that in the case where this discard bits thing. Well, no, this is always masked. So yeah, we should never be able to get that back, right? If we only ask for that many bits, we should only be able to get something back that's less than the entry count. So we're going to assert that that's actually true. And then, because if it's not, we just know our code's broken at that point, like whatever we did. So then what we're going to do is we're going to take a look into the Huffman table. I don't know why I put that in result. It's not result. It's entry index. Right? So I'm just going to look through here at entry index. I'm going to pull out whatever this Huffman entry is. So I grab the entry out of the table. It's got the symbol and the bits used in it. So now I know exactly what I need to do to produce my result, right? It's just, oh, the entry is the symbol that's in the table at that location because that's what I've packed in that table. And then the number of bits that I need to suck out of the input stream is just the other entry in the table, right? So I know how to say discard this many bits because the entry itself says how many bits to discard, right? Easy peasy, lemon squeezy, no weirdness there, right? So you can see why I said this was the fast and stupid way. It's because there's like no code to it. So it's probably reasonably efficient. The only problem is you've got this big bloated lookup table that has a ton of entries for the same symbol, right? Small symbols that are encoded frequently have like 50 million entries in there. And because, it's an 8-bit symbol, but you've only got 1 bit to encode A, so that exists 128 times in the table, right? For no reason. But there you go, right? I called it stupid, right? So anyway, there's the Huffman decode step. So all we need now is something that actually fills in the table. And that means we need to have something that actually does that value replication. So there's two steps to this. The first thing is figuring out what the code lengths are and assigning those codes using the code lengths via that weird structure that we read about in the spec. Then the next step after that is to actually flood the Huffman table with all of the symbols in the right positions that are indicated by their symbol lengths as given by that, that input set we're talking about, right? So that's what we want to do here, and I think that's probably... So I think that's probably just a case of running over the input and spamming out those symbols into the table. I'm just not sure what the most efficient way to do that actually is. So I think we just do it directly. So we got the part at the top that's going to be based on the PNG spec nonsense that we'll go read. Deflate spec nonsense that we'll go read in a second. But I think then all we have to do, right, is loop over each symbol. We know how many of those there are. So really it should be this. So we know how many symbols we have. We know what the symbol code lengths are. So we need to do the thing that turns symbol code lengths into actual symbol codes. But once we know that, for every symbol index that we have, we know that we have the symbol code length in bits, right? For that symbol. And we also know what that symbol's code is. That's the part that we don't know. So we need to figure out that as per the PNG spec. Once we've done that, we will have both the length of the symbol and its code, right? Once we know that, then we should be able to spam that into the table everywhere that it should go, right? So if we take the entry count, which is the number of places this will be in the table, what we know is the entry count is exactly the inverse of the code length in bits, right? So if I know that the total entry count in the table is X, right? And I know that the number of entries this one will have, is that shifted down by the number of code bits, right? Because this thing will occur in the table however many, I'm not explaining this well. Usually when I'm not explaining it well, I need to go to the little drawing board, so let me go. So, like I was saying before, I've got a Huffman code for this thing. I don't know what it is. It's, the Huffman code for this thing is like 01 or something. I don't know, right? So it's 2 bits long. But I know that my symbol table, right, or something is 8 bits long. So I know there are 6 bits here that no matter what they were, when I read this thing in, as long as I saw that in the bottom, I know that I output this symbol, right? Because it's got to be that. It can't be anything else because I just said that if I see those 2 bits in a row, that means this symbol. Huffman table is over. Truncate the rest, right? So this 6 bits can be anything. What that means is 1 shifted up by 6, right? Or 2 to the 6th power, right? Which is 64. I know that many other places in the table it's going to be because any arbitrary combination of these 6 bits that has this on the bottom How many are there? Well, there are 2 to the 6th of those in the 8-bit table, right? It's all of the entries with a 0, 1 on the bottom and any other 6 bits on top, right? So all I have to do is enumerate through all those 6-bit values, shift up that amount or in the actual code on the bottom and spam it into that location of the table, right? That's it. So that's all I would have to do. Now, if I wanted to do this more cache friendly, what you could do instead is, nah, you know what? I don't care. Not gonna do that. All right. So anyway, so the entry count here is just gonna be one shifted up by the remaining bits, right? So the what do you want to call these? Arbitrary bits. Right? So how many arbitrary bits are there? Well, the number of arbitrary bits is whatever the Huffman table says there are, right? So the max code lengths in bits. However many bits that is, I know I've used this many bits. So however many I have left, that's how many must be arbitrary. So the number of entries is actually that. So the entry index for this particular symbol is going to be that many entry that's how many there are. So what I'd like to do from there is say, all right, whatever the entry index is, I know the code length in bits is used at the bottom. So let me shift the entry index up, right? Let me OR in the code for this, right? And that is where this thing goes in the table. Like so. So now I say, well, now we know what we're talking about here. I know the bits used. I can actually do this, I suppose. And so then what I could say is, all right, the bits used is the code length in bits, and the symbol is just the symbol, right? It's whatever one we're on. Now, I don't know if we want to also pass in an array of symbol values, because it may be that the symbols themselves that we read back want to be shifted automatically by the table instead of having to add a number to them. So what we could do there is specify a pre-offset or an increment or something like that. We could make it so that this is encoded a little bit differently. We'll see if we want to do that here. Like what I could say is, you know, an addend here that's equal to 0. So normally it just doesn't do anything, but in this case, you know, we can just do that. So the symbol that we record is actually shifted up somehow. So because like you saw a lot of things in there where like, oh, it's the symbol value plus 3 or something, right? Well, if we know that the symbol value is plus 3 ahead of time, we could just bake that in the table. I don't know if we'll ever have occasion to use that. It may be that the way they set it up just doesn't actually admit any particular way of doing that, and so in that case, we wouldn't really be able to do anything. But we can deal with that a little bit later. So anyway, when we do our symbols here like so, what we can do is also ensure that ones that we don't use, like symbols that don't get used, we can ensure that those are cleared, if that makes sense. Well, actually, I guess they wouldn't occur, so it doesn't matter, right? So that should be fine. Anyway, so I think, if I remember correctly, if the code length in bits is 0, then that means that this thing never occurs, because you can't have one of 0. It has to have a code length of at least 1. So what I'm going to say here is just that, all right, if we see one that's 0 length, we just skip it. We're not going to do any more processing on it, right? So that, I think, is the thing that spams our Huffman table, barring typos or omissions that I made in there. That's the thing that generates the Huffman table once we know what the codes actually are. So at that point, what we're left with is we need to have some way of building those codes. We need some way of actually interpreting the algorithm that we saw up at the top, which is that, not that, is this. We need some way of actually implementing this algorithm, which is going to tell us what the codes are as opposed to just their lengths. Because remember, all we get as input are the code lengths, and using the rules that they have specified for determining what codes are based on their lengths, we're supposed to regenerate the table ourselves for obvious reasons, so that we don't sit around specifying a bunch of things that we didn't actually need to specify. So let's see. Count the number of codes for each code length. Let BL count be the number of codes to that code length. So that seems pretty easy to do if we want to. That would just be something where we go through like this. And we say code length count, symbol code length, symbol index, plus plus, right? So this is some kind of an array, and we would have to clear it to 0 first in order to count it properly. We would then go through all of the code lengths. We would see how many of them we saw, and off we go. Now, we can actually do this right on the stack probably because the number of code lengths cannot be longer than the longest code length. We know that 16 bits was the longest code length that we could see here. So what we can do is just say, look, that's what we're counting. We know we're never going to see more than that, right? Furthermore, I can do PNG Huffman max bit count or something like that, and just define that as 16. So it's easier for people to see where that 16 comes from, and they don't have to sit around wondering what on earth we're talking about as we go, right? So the other thing I can do is, I believe we sort of made an assertion on that in here. We can also make that assertion, right, depend on the Huffman max bit count, right? All right. So it's free for me to just do one of these because this is tiny. It's only a 16 entity histogram table. And you know, I could call this code length histogram just to make it a little more obvious what it's actually doing. So as we come through, we clear all that to 0. We look at all what the symbol code lengths are. We increment. And what we could do here as well is again, just take this count and assert that the count is less than or equal to the size of the table, which makes it so that if anyone generated us bogus data, we would at least sort of break in here in the debugger so we could go, what's going on, right? And if you were trying to do an industrial strength one of these, you would actually generate an error here or something, right? If you were trying to make this for like Photoshop or something where you wanted to present an error to the user that the file was corrupted, right? You'd put that in here too. So anyway, when we go ahead and implement this symbol code thing, that's the first thing we need to do. Figure out what all of the code lengths add up to, how many we've seen of each of them. That's what they're telling us we want to do first. So we did that, right? We could, they're telling us not to count zeros. We could do that. We don't really care though. So we'll just count how many zeros are anyway, and we just will throw the value away, right? We just don't have to use it. So the 0th entry in the code length histogram will be counted. There's no reason not to count it. We just end up with a branch in here for no reason because we can just never look at the value, right? So it doesn't matter. So what they say is they want to find the numerical value of the smallest code for each code length. And that seems pretty straightforward, right? We just go ahead and search through them. I don't really know why you need to do that. What? Find the numerical value of the smallest code for each code length. But why? Why couldn't you just go through the table directly? I'm a little confused. I apologize. Find the numerical value of the smallest code for each code length. Oh, I see what they're saying. Okay. They're just trying to say pre-compute the starting value. But, okay. When they said find, I thought they meant that there was something like searchy about it. But I'm just like, it's always just the same. I mean, there is only one value that it is, right? So I was a little confused there. But when you look at the actual loop, they're not searching for anything. They're just putting in what those values are, right? So that seems pretty straightforward, actually. I'm not sure. I also can't quite tell why you would need the BL count value there. So that's confusing because why wouldn't you do it the other way around where you just increment the bit code from 0 each time so that you don't have to do the count first? Am I the only person who's confused about that on the stream? I mean, correct me if I'm wrong, but if you just went through the table in order, set each of the bit count fields to just be the first value that is allowed for that length? No. I see why. It's because the Huffman table is free to be balanced on either side, right? So they could choose. They want to be able to balance the Huffman tree however they want for obvious reasons. So you need to look at how many there were because that lets you know whether or not you ever used a particular code sequence because you could assign it to some other code. Right? So like, for example, if you never use a 1-bit code, then you're free to use more 2-bit codes because you can use both values of the bottom bit, right? But if you used bit 0 as an actual code, then the only 2-bit codes you can have are ones that have a 1 in the bottom, right? Or something like that. Do you know what I'm saying? They're using the other direction here, so I guess that's a bad way to say it. So this is the high bit, right? But so okay, that makes perfect sense. I understand what they're doing now. I don't like to just like type something in if I don't know what's going on because like, well, I don't like having a bad understanding of it. So it was like if I know there's an error in my thinking, or maybe the spec's just stupid, I don't know. But in this case, there's an error in my thinking. I want to correct the error in my thinking first before kind of plowing forward. All right. So once you have the code length histogram, then this is pretty straightforward. We can probably just like it seems like you could just obliterate. You could do this in the same array. Now I won't because I want to be able to look at it. But I'll just say like, note Casey, you could do this in the same array if you wanted. So this one, I guess, doesn't really have to be assigned to anything in particular here, right? This next unused code, I guess, doesn't really need to be cleared because everyone who has been seen at all will actually get a value assigned now. So that seems straightforward enough. So if I go through the bit index here and I just loop through how many of these there are, right? I think, like I said, so they use BL count bits -1, and I guess we could do that too, since I guess we're not gonna, like, normally I think you just keep a run, but, you know, whatever. So we assume, like, when we did this summation before, we assume that the 0 doesn't have any, because like I said, even though we counted it, we don't actually want to ever use it. It looks like they did the same thing here, right? So off we go. We start with a code of 0, and each time here, what we do is we look at whatever the previous count was, we add the code that we actually generated to it, and we shift up by 1 because we're adding another bit in there, right? So we basically say, okay, whatever our code length histogram was, also the bit indexes start at 1, right? Yeah. Because we're looking backwards one in the table every time, so we can't start at 0, right? So we look backwards at the table, we find out how many of them there were in that, so we have to advance by that many codes, and then we shift up 1 for the fact that now we're adding a new bit, right? So that's what the code is, and then the next unused code, right, is just that. Now, I feel like it's a little weird that they chose to do a running tally for one and not the other, it seems like to me. So, you know, it just seems like you would probably do this, wouldn't you? Just to be consistent, I mean, that's the way, that's their idea, not mine. So I'm not sure why they had code be a running thing and not next unused code, because it's just like, it's okay, it's whatever the previous one was, right? We make the new one out of that, and then the next time through the loop, we just keep using it, right? So it seems like that's the, you know, that's the sane way to do it, right? So then we know what all the symbol codes are. Rather than spam those out, since we now want to know what the symbol code is here, we might as well just generate it right there. You know what I mean? So instead of, right, because there's no point in us building another table of symbol codes when we know we don't care what the symbol code is. We're just going to spam into our Huffman entries based on that symbol code. So we can just create it right here, right? So we can just do this, right? This loop is the same as this loop here. So we are doing exactly it. We're doing exactly that as well, right? So all we need to do is actually assign the codes here. That's all we need to do. So we know what the code length in bits is. So if we just say, all right, once we have that code length in bits, we know that that has to be able to go into here, right? So I can assert that. Right, so when I pull out the code length in bits, it had better be able to be into this table. And then what I can do is say, well, the code that I actually want is just whatever the next unused code is for this code length in bits. And by the way, once you grab that, increment the value because the next person who uses it's going to have to use a different one, right? Then we just continue right where we left off. Now we know what the code is. We can just use it, and off we go. I think that's all of it, right? Like, I don't think we need to really do anything else to assign the bits here. I think you're pretty much just done. So yeah, so I'm fine with that. I think it's fine. So yeah, I guess here the other thing I would want to do is say, well, let's just make sure that we don't exceed our bounds. So let's make sure that when we upconvert these guys, we ended up with the same thing that we expected, right? And that's all there is to that. So I think we're done with that part of the code, I think. I mean, again, that's just me reading the spec and trying to guess at what they mean everywhere, but it seemed pretty sane. And so barring like us making typos there or me saying I was doing something and not quite really doing it, which obviously happens all the time when you're programming, I think we're roughly in the ballpark there of, you know, what needed to happen for that, right? So I think all we need to do from here on out is actually go ahead and, you know, make these Huffman tables. Since these are going to have to be freed, I'll go ahead and put a little free in there for these. Well, actually, you know what? I'm not freeing, so it's okay. I'll free at the end. We'll deal with that a little later. So the Huffman decode and the Huffman allocate part of this, we now have to make sure actually follows the rules that I set. So when we go ahead and do an allocate Huffman down here, we need to allocate them so that they fit the number of bits that we're actually going to see. So in each one of these, we need to do a Huffman allocation here, like so, that has the right number of bits in it, and then we should be good to go from there. So these Huffmans, I don't really know how long the symbol lengths are going to be, so I'm not sure. For this one, we know that they have to be only 3 long, right? Or something? No, how long are these guys? Yeah, so these are 3 bits long. The symbol lengths, it looks like. So I think this Huffman is just a 3-bit Huffman because it's only allowed to get 3 bits for each symbol length, so that's the maximum, right? For these other ones here, I'm not sure. This table is just one big table. So it looks like this one's just 15, right? Because anything that's up to and including 15, that's an actual length. Everything else is not. So I think this table is 15. What do I got here? I got a list len Huffman and a dist Huffman, but they're both the same, right? And it looks like they're each computed as a separate Huffman table, I guess. We'll see about that. I'm not 100% sure. So then we do our little happy dance here, and then we've got, okay. So at this point, we need to go over this whole routine again because I want to actually inspect that here. But at this point, we have actually written the whole decoder for the deflate part of things. There's another step we have to do after this, which is untransforming. So there's a little bit more to the PNG than this. According to the spec, there was the filters. So we have to implement the filters, but we're basically there on the deflate step. And so now we just have to go through and actually fix all the bugs and stuff like that, and and what have you. But anyway, let's go ahead and step through this and just see where we're at. I don't remember where we're at on time today. I think we've got a while. 30 more minutes, probably, something like that. I'm not quite sure, but something like that. All right, so if I go ahead and step into this thing, I can just get a sense for whether it's working at all, which is all. Like, I just want to see if we've roughly done anything resembling anything, right? Let me actually go here. Okay. So here's our hclen table. I'm not sure whether it's all correct or not, but there's the swizzle, here's the table, here's the bits we consumed. So here's what we got. It's plausible, but then again, anything would be, because we're only reading 3 bits at a time, so there's no real bogus values that can really get in here particularly much. So anyway, now when we go to compute the Huffman, let's, okay, so we're allocating 1. How many are we allocating? We're allocating 8. That's exactly what I would expect, right? Because it's a 3-bit Huffman, so in theory, if you can only have 3 bits, there's no way to get outside of the 7th entry, right? Or the 8th entry, 0 through 7, right? So when we come in here to compute Huffman, here's our code length histogram that's set to 0. So what I want to do is jump past that histogram computation, and then I want to look at the histogram. Here's what we see. 3 values had nothing. The rest of the values, okay, there were some 3s, some 4s, some 5s, some 7s, and that was it, right? That's what we saw. Now, does that comport with what we actually see in the data? I don't know, so let's actually take a look. I don't remember how many of these we have, so tell me. Oops, symbol count. We had 19 symbols. So let's see, 3 7 7 7 5 5 4 4 3 3 3 3 4 4 7 5. So we should see 3s, 4s, 5s, 7s. That's it. 3, 4, 5s, and 7s. 3, 4, 5, 7, and that's what we saw. Perfect. So then we come through here and we start to assign these codes. Let's go ahead and look at what the codes we're going to assign are. Here's next unused code. We know that this is an array that has sort of the the number of bits as the parameter there. So we're going to go through and assign those. And what we will see, hopefully, is we will see these assigned only to the values where actual things need to occur. There we go. So yeah, So I guess I don't know if the rest of the table is meant to clunk up that way. They did it. I mean, that's what they did. So they don't if 0 around that. And so I assume they just want to fill it because they're never going to use these values. So these are just bogus values anyway, but they're there just to make sure it's clear when you get up to the higher bits that actually are used, if they are used, that you reserved, that you kept shifting it up, right? So I think that's fine. I think. So let's go ahead and see what we get for codes here. So the first symbol index 0. Where's our symbol code lengths? Here we go. Is a 3, so that means we should actually process it. What is its code? Its code is 0. Is that right? Apparently so. Think that through. Yeah, I mean, that actually does seem right. But wouldn't it have to start at 1? You know what? No, it wouldn't have to start at 1 because they're pre-saying, in fact, they showed this. They're pre-saying that what they do is they leave the 1 value as the repeat value. So it's the highest value that's not used, not the lowest value. So yep, that's on the table. Seems fine. So the arbitrary bits here, code length in bits is 3. Well, there's a bug right there. We forgot to initialize that value, so that's not going to go far. That's not going to have legs. So when we allocate the Huffman, I need to actually put the max code length in bits in here. Sorry about that. Let's try that again. So right back to where we left off. The arbitrary bits here, the max code length in bits is 3. The code length in bits here. So that's not right either, is it? I computed that incorrectly. The max code length in bits in this case is not what we actually want. So those are two. So those value that's not what I meant to say. So max code length in bits. It's. So this value here, the max code length in bits that we're talking about there was talking about how many bits would be used to encode a bit length. But it's not the actual number, the highest number that can actually be. It's not the highest Huffman code length at that point. It's the highest, it's the number that encode, the highest number of bits you would need to encode the count that is the bit length. Does that make sense? So actually what we want here is just the entry count. The max code length in bits, I guess, is not relevant. Am I wrong about that? Yeah, so this is not the correct value, right? What we actually wanted to know is how many bits we needed to read, which is actually the entry count, right? trying to think of what I messed that thinking up. You know what? No, I didn't. Okay, so I take it all back. I think the only thing, so after looking through it, I don't think I did. I think the only thing that I did wrong was saying that this was a 3. But it's not a 3. 3 is how many bits are specified for the code length, right? But the code length is therefore 8, right? So the number of entry counts you actually need in the PNG Huffman is the value shifted up there, right? So it's like a double shift up, I guess is the way to put it. So like if I say that it's 3, the max code length in bits is 8, right? And the entry count is 256. I believe so that was where I was kind of going wrong there. So in the allocate Huffman, this is actually a little bit, this is kind of bogus. Really what we want for max code length in bits, this was actually specifying max code length in bit, right? Is what we actually passed in. So it's actually this. And it gets shifted up, right? Then to get the entry count, we have to shift it up again. So I think that was just I kind of like elided those two things in my head because it was just getting a little squinky. So let me try that one more time. And I think now we're in better shape here, right? Yeah, and well, I mean, I guess the other problem here, so those other ones are specified wrong. So I guess the other thing is I could do is just actually do this and change the specification for that one. Because I think, yeah, these I specified the actual bit length, right? Which was 15, and here I specified the bit length, which was 3, right? So maybe the right thing to do is just specify this one as 8. But like those have to be the same, I guess, is the right way to say it. Okay, so now we're subtracting 8 from 3, which is what I actually wanted, which gives me 5 bits arbitrary, which means that this goes into 32 places. We're going to spam it like so. So we say whatever the entry is shifted up by the code length in bits, which is 3, ORed with the code. We slap it in there, and then we keep slapping it in there a bunch of times, right? We do all that, and then we should actually have our Huffman now. That's the result. So here's our result. We have 256 entries in theory. And so if we look at what they all are, we should see like, you know, a bunch of these all are 3, right? So like, this one's 3, that's 3, etc. It looks like for some reason we've got codes that aren't used. I think maybe that means we've got a bug in there, right? Presumably all the codes should go to a valid symbol unless there's just empty space in the table, which there might be, right? Because it might be that you don't need to use all the codes because you don't have an even number. Like Huffman tables maybe get balanced in a certain way that mean there's some things that just you don't ever get, right? Or something like that. I don't know. Although I guess now I think about it, symbol 0 was a real symbol. So, but bit 0, sorry, wasn't. So yeah, so bits used is 0. So one thing we could do there too, you know what? How we can check to see if we've got a bug there is also we can assert in our decode Huffman that we never have that case. So inside Huffman decode, I'm just going to assert that bits used is not 0, right? So that way, if we do encounter a symbol that we really shouldn't have shifted, we'll know that that was an empty space in the table, and so we just screwed up when we made our Huffman table, right? All right, so if we come in here, let's see what we get when we encode. All right, so yeah, so we've got a bug there, right? Now, there's a couple different ways we can have a bug there, and I'm not sure which one we have. So when we are shifting bits in, one of the problems that we're going to have here is that we have to make sure the endianness matches up, right? So when we're gathering bits from the input stream, we have to make sure that those bits are put into the value that we're looking at in the same way that the person who wrote the spec thinks they should come in, right? So if they think they should be shifted onto the bottom and we're shifting them onto the top or something like that, then we're going to have incorrect results, right? So the first thing we should probably do before we even look at the Huffman table stuff is now we have to actually get serious about the bit consumption stuff, because we really don't know how that's going. And we should probably try to make sure that we do have an idea there. So let's first look at that part and get that right. So let's see. So I'm going to read section 311 carefully, because that's the part that talks about this, or at least should talk about this. This document does not address the issue of the order in which bits of a byte are transmitted on a bit sequential medium, since the final data format described here is byte rather than bit oriented. However, we describe the compressed block format in below, is that a sentence? As a sequence of data elements of various bit lengths, not a sequence of bytes. We must therefore specify how to pack these data elements into bytes to form the final compressed data sequence. Data elements are packed into bytes in order of increasing bit number within the byte, i.e. starting with the least significant bit of the byte. Data elements other than Huffman codes... Oh, so it's backwards. Data elements other than Huffman codes are packed starting with the least significant bit of the data element. Huffman codes are packed starting with the most significant bit. So it's the opposite. If one were to print out the compressed data as a sequence of bytes starting with the first byte at the right margin and proceeding to the left, with the most significant bit of each byte on the left as usual, one would be able to parse the result from right to left with fixed width elements in the correct MSB to LSB order and Huffman codes in bit reversed order with the first bit of the code. Okay. So does that mean that I have to have two different ways that bits get consumed, one that packs one way and one that packs the other way? Or is there some way I can more... So that is... So there's one of two things that's true now. Either when we go to actually write this code, it turns out that that ends up being a convenient, good thing to do. And so like it's fine that the spec was written that way because it was just written so that the implementation would do some efficient thing. If not, WTF, man. Why would you pack bits one way for one thing and the other way for the other thing? Why would you have two different ways of packing bits? Does that make any sense? So hopefully that's just something that when we actually go to do it, it's like, oh yeah, it's like makes sense. Like that's what you would do, right? If not, then WTF. So anyway, all right, let's take a look at that. How we're processing our input stream here. All right, so when we go to bring bits in, we're going to read a byte. And then the byte, what it's saying is that normally they're packed least significant bit to most significant bit, I guess, right? Which means that if we just look at the byte, we got what we wanted, right? I mean, that looks like what we're saying. So when we consume a U8, if we read the bits from the bottom, it sounds like that's correct. That's what we should do, right? So if we consume 3 bits, we just consume the 3 bits on the bottom, and they're in the right order, with the least significant on one side and the most significant on the other, right? But if we were to consume them for a Huffman code, it's basically saying that they're backwards, right? So I think that means we have to invert the bits the other way around. When we go to put them into the Huffman code. And I don't have any, I don't know why. Right? I don't know why we would do that. I don't even know what that means now that I think about it, because since you're creating the Huffman codes yourself anyway, why would you care which way they went in? Just give the way you build the table and it won't matter, right? But yeah, that seems really unfortunate, because so we know that at least some Huffman codes are 15 bits long. So that means they will have to read 2 bytes. The bytes that we read in, then the bit order for the Huffman. So what does it mean if you read 2 bytes, but you want the most significant bits first? Do they want you to read the bytes in the normal order? I assume so. So as we read a byte at a time, we're just talking about for the Huffman codes, we read off of the top rather than the bottom, for who knows why. Just because we do. Well, all right. So if that's the case, then the most efficient place to do this is to make the table backwards, right? So it seems like, while I have no idea why you would do that, then the most efficient place to handle that would be here. So I was making the code with the assumption that the most significant bits were in the other place, and here we're sort of assuming the opposite of that. So I guess the first question I have is, when they said this right here. So when they said this, is this creating the Huffman code that way? Or I assume the answer is no, because I assume this code they're giving me the pseudocode for the wrong Huffman values, right? This is the pseudocode for the backwards, the way that the Huffman codes would be generated in your CPU, but then they're basically saying, well, we're gonna pack them the other way round, right? I mean, that sounds like what they're saying, and maybe I'm way off base on that, but that seems like what they're saying. So then when the bits actually come in, and they come in this order, right? I need to flip my thinking about the bit order when I do that lookup. So I guess, and maybe I might be totally off base here, right? And this is why I say this spec is not particularly good. I guess what I'm trying to do then here is say, okay, well, this packing into the table should actually pack the other way. When I look at the index and I say this index has my bits going in the reverse order. So I actually want those bits like flipped around, right? Yeah. Right. So when I look at the code, right, this code is backwards. So I guess I'll write something that flips the bits here. In a really inefficient way. And then assuming that we get that working and we see that that really is how the Huffman code is encoded, then I will go ahead and actually try to make it more efficient because we don't really need to do it this way. So if we go through and we say each individual bit that we're talking about, right, it's free for me to invert this because what I can do here, oh, actually I can just put this in here, right? So this is really slow and, don't do this at home. So what I can do here is when we say what the index is, I'm just going to reverse the bit pattern of the index. So for each one of these, I'll just say like, okay, the index ended with 1 here. So or in whatever the base index value is that I have, what I want to do is for a particular bit index, right? I want to shift it down to get that bit out. I can, by the way, do this for only half the bits because we're just going to flip them, right? So I can take the base index, I can shift it down by that bit. There's also probably an intrinsic for this, but that's beside the point. I can shift it down by however many bits I'm doing. I can AND that part and then shift it up by the opposing number, right? So what that's going to do is that's going to put, bit 0 will go in the bit 15 slot, and then bit 1 will go in the 14 slot, and so on. So it'll just invert, right, where they are. Again, not really sure that's what they wanted me to do, but it's what it sounds like they wanted me to do. So let's take a look, right? So here I'm going to just go ahead and look to see to what extent I actually successfully flipped this. So let's just take a look at some of these here. Oh, and I need to know how what my actual max code length in bits was. So it's 8. So 1, 2, 3, 4, 5, 6, 7. Well, you know what I can do. So here you can see us flip them around. So now this was the fourth byte in, and it looks like I'm off by 1 there, right? 001, that should have flipped to that position. So I think I actually need to do that. There we go. That's more flippy. That's wrong. Oh, duh. I obviously also need to do the corresponding bit flip. Sorry. So I'm just going to take this value here. There we go. So yeah, looks like we're flipping now. All right, so that's like, you know, our flipped Huffman table. So in theory now, that is like sort of what we're actually talking about, I guess. So if that's really what they meant, then we're going to have the bit patterns packed in the opposite way. And the reason that we have to have the bit patterns packed in the opposite way is because that now means that when we look at the actual value, it's going to be packed around backwards. The further complication, at least I think, if I'm not very much in error, is that now when we consume the bits, we have to pack the bits onto the top, right? I guess the other way we could do this is flip before we look up the bits. That seems really inefficient though, because you want the table to do that, right? So I feel like you want to be able to yeah, now that I think about it, I'm not even sure you can really do that. Because it seems like you'd have to just flip the bits of the code every time. Because when I get new bits in, normally I'm sticking them on the top. No, that should still work. So this should still work because, yeah, like I'm just looking at that value and saying, well, they're telling me it's most significant byte first. So it just means that when I actually look it up in the table's like flipped around, right? So I think that's okay. So let's investigate further. But this is the part that's going to be really annoying, right? Because we have nothing to go on. Like, we just have to read the spec and go like, I don't know. Like, seems like this is what they want. But we'll see. So anyway, let me jump down here and see what actually happens. Let's go to peak bits. So we know that we want 8 bits. I'm not sure how we got a bit count of 1 in there. I guess that was one we didn't use previously. But anyway, so we're going to consume a U8 and get some more bits in here. So now there's 9 bits in there. And we're just going to take the bottom bits of that thing. And we have not underflowed, so there's our result, right? So we got back a 95. That's the value we're going to look up into our table. The table that we get there is symbol 10. It says that we use 3 of the bits to decode symbol 10. So we say, okay, then we're going to go ahead and discard those 3 bits. And that's all fine. So then we do some nonsense here. We don't know if any of this is correct, right? So we'll ignore that for now. So then we come in here and we want to look at the indices again. Now we get 75. What's our entry this time? It's another 10. Who knows if that's right? Like, we don't really know. We should probably try to get some known good data in here that we can use to decode and check. But okay, we keep shifting. So off we go. So question, when do we actually hit our first error? Because I don't actually know when that happens. So eventually we hit an error here where we hit a symbol that we shouldn't hit, right? That wasn't encoded. And our problem is we don't really know. We have no idea whether the first set of things we decoded was right at all. Like, we have no idea. We're just getting some data, and it could be right or it could be wrong. And that's all we have to go on. So I don't know how many times we actually... it looks like this is not... Yeah, so this loop is busted. So I don't really know... so I don't really know how far along we are yet. So we'll see in a second. Anyway, this lit len count and the len count, this is how many we're going to get. So this value should be incremented, but it's not clear to me that it ever was. It was set to 0, which doesn't really make any sense. Because, so the len count's going up here. So this, I feel like this is busted, right? I feel like this is supposed to be lit len count here. Because this was never getting incremented. Similarly, this is supposed to be the prior one, like that. So I think len count should never be used inside this loop. So that was just a typo. All right. So let's try that again. And now I want to see when we crash out, right? Because now when we get the wrong symbol, I just want to know where we were. So we're on like symbol 11, right? So let's also see, I'm going to try it both ways here. So since I really don't know what they mean by this, if I don't do this, when do I crash out on the non-reversed version, right? Okay, so the reversed version, if only by accident, definitely gets us further through the process, which suggests that that is more correct. They do really mean that they reversed the bits just for no reason. Like, who knows? I don't know why they reversed the bits. They just did, right? So yeah, that's pretty special. So I don't know. All right, that's the end for today. Tomorrow we'll pick back up at that place. I'll go to Q&A now. But yeah, I also think there was somebody had posted an issue on the GitHub about a typo. I can go take a look at that now. I don't really remember what it was, but I think that someone had an issue that they mentioned. So let's see. Wrong value in lit len dist table for value of 17. The implementation says 3 bits of length, but you typed, copy pasted, consume bits of 2 for the encode len 17 case. Let me go ahead and get that. Yeah, we have to like check this whole thing. So this should have been a 3 here, apparently. Right? Yeah. All right. So anyway, I don't think that affects, I think we're still wrong at 11 anyways. So we still have to kind of look at what's going on here. And again, I don't really know how right this is at the moment. So we've got some work to do there. We don't even know if we're unpacking the Huffman correctly. Like we know nothing, right? But anyway, I'll do this. I'll retire this to do here as well. So day 455, close the comment. All right. Let me look at the questions now. Ratchet Freak, don't the bits when reading the table need to be reversed as well? Don't the bits when reading the table need to be reversed as well? I guess I don't know where you mean. Can you be more specific about where you think the reversal should be? How many hours long is the series? Miblo can probably answer that question for you. I'm not going to talk about Vulkan's error handling now. That's really pretty far off topic. You said multiple times that PNG Spec does not allow fixed Huffman codes, but this is not true. PNG Spec explicitly says that both fixed and dynamic Huffman codes are allowed. Oh, okay. So we might get that then, I guess. Oh, did I have a typo there? This is why I always use macros for that normally. I don't like using malloc. Thank you. Because of exactly bugs like that. Like you notice in Handmade here, I never allow that sort of a thing to happen. Because if you do it like this, you can never have that bug. But if you do it like this, you can have it all the time, right? We'll move it over to that when we get there also. So let me go look at section 10. Martin says it allows that. I thought it said it didn't, but I guess I was confused. Where is it? 10.1? You're right. So right here, it says fixed Huffman codes. Ratchet Freak, when reading the 3-bit lengths, you'd read, for example, B011, but I believe it should be B110. So is that really true though? Because the spec, at least as far as I can tell, suggested it's the other way around, right? So it says data elements are packed into bytes in order of increasing bit number within the byte, starting with the least significant bit of the byte. Data elements other than Huffman codes are packed starting with the least significant bit of the data element. Huffman codes are packed starting with the most significant bit of the code. So doesn't that mean that only the Huffman code would be reversed? That's how I read that. Do you read it a different way, Ratchet Freak? And by the way, Ratchet Freak, I'm definitely not trying to state that that's the case. I'm just saying that's how I read it. Like I said, this is the first time I've ever looked at the PNG spec, even a glance. So I have no opinion on the correct way to read it. I am just doing my best from the verbiage they placed in here. And at least it seems like they are literally saying they chose to pack bits in two different ways. I don't know what the reasoning is behind that. It might... You know what? I just don't have any idea what the reasoning is for that. Because you can choose to interpret the Huffman codes either direction when you're actually building your Huffman tables. So I'm not sure why you wouldn't have just picked the same way for uniformity, but I'm not a compression guy, so maybe there's a very obvious reason that you would know if you were, right? Ratchet Freak. Yeah, you are correct. Well, I don't know that I'm correct. I just know that that's what this says. So that's the reason I didn't reverse it everywhere else, is because it seems to suggest that the way that we're reading bits currently is correct, but not for the Huffman codes. So we have to have a way of reversing the bits for the Huffman codes. The thing I'm not quite sure about is when we are shifting in those bits and looking at them, I don't know if that means we need to shift the bits in the opposite order somehow. I think I think what I'm doing right now, I don't think it works to just reverse just the table part. So I think we might be SOL on that. And we might have to like shift bits in and flip them or something. Right? Like that's a hard thing to work out in my head. I got to think about it a little and maybe draw it out. But I don't know if just flipping the table that way actually works. It works for one Huffman code. The question is just when you then shift bits in, I think you're shifting the wrong bits out. Does that make sense? So I'm pretty sure we can't do that because we used a different bits than left. Possibly. Is that true? No, it might be okay. Might be okay. Yeah, it might be okay. I mean, something's wrong because we're not parsing it, so we know that at least one thing's wrong in there, you know? But the question is just what? And we'll try to find out tomorrow. Only Huffman codes are bit reversed when looking at the bit from the first byte to the last, and most significant bit to LS. Right. And at the moment, I think since we're only looking at bytes at a time, we don't have a byte boundary reversal problem in theory yet. Although maybe we have that too, you know. So we gotta, like I said, we're gonna have to dig in here and figure that out. All right, well, if there's no questions, I can close down the stream. Thank you everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you want to follow along with the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can play around with it yourself. If you want to see the exciting conclusion of how to interpret the Huffman codes in a PNG file, we will be back here tomorrow, same time, same place, to do exactly that. Hope to see you back here for that. Until then, everyone have fun programming, and I'll see everyone on the internet. Take it easy, everybody.